Hello, good afternoon. Welcome to the stream. Today, I am excited about our next step today. We are going to take our Lisp-like language that we've been noodling on, and we are going to lower it into a C-like language, like we've done at least 3 or 4 times before. In this case, remember we have added in chapter 6 is all about a heap allocation and vectors, which are basically structs in any other language. And we have what was I going to say? So we've gotten so far to the point of doing all the transformations in that Lisp-like language or variant thereof, and now we're ready to translate into something that's more imperative. So the C-like language is alternately called 3-address code because it's usually like variable A equals variable B, some operator variable C. It's in that kind of form, and there are different things that happen at that level of like a statement. So we're explicitly ordering statements at this point, as opposed to having an implicit order based on left to right evaluation. So now we're going to make it explicit, and we're going to translate all of our new stuff that we added in this chapter, so the vector definition, the extracting fields from vectors, setting fields in vectors, and allocating and garbage collecting. Those will all go into our C intermediate language. I say C. It's C-like in the sense that it's imperative, and it has constructs which are very, statement by statement. Okay, so let us jump into it, and we will likely have to first define that C-like language. So here's where we are. We're starting chapter 6, section 6.5 of chapter 6. And this is explicate control. So in other words, the explicate there being make it explicit, right? And control is about what is the order of operations. So previously we have handled taking the monadic form of the Lisp-like language and turning it into the C form. Note that this is an older version here I mentioned. But what we can do is we can jump down here and look at what is the abstract syntax of the C tup language for tuple. So we have ltup, we have their intermediate form, which islalloc and lmonalloc, and now we have ctup. So what I'm going to do is the latest one that we did was cloop in the last chapter when we added loops and mutable variables, and we're going to call this ctup because all of these are additive. We're just going to be putting new forms into the language. So all the things that applied before still apply. Okay, so we are not adding any tails. We are adding expressions. So we need allocate, which is going to be amount in int, and we'll say t is going to be, let's import ltup here, and we're going to import the type. That isn't a mouthful. Okay, so this is going to be a type. I don't know that at this phase that we really need that. it would be fine, I think, to erase it. But here we are. We're going to keep it. Okay, and then we have some primitive operations. So we have vector ref, vector set, and vector length. But also at the expression level, we have global value. And that's going to be a var as a string. So it's just a reference. Okay, so we have, similar to read, we can have vector set in a statement position, which is fine because vector set returns void. But we're going to have to do like we did here. This is a read statement. We will have to do vector set statement. Let's go ahead and vector set statement. And I'm going to leave that for now. We're going to fill it in a second. And then collect amount is going to be an int. Okay. So vector set. And I think that what we did in Elmon alloc is that vector set, yeah, it had just had 3 atomics. And we've already enforced at a higher level that that index has to be an integer, like a literal integer. So we shouldn't be able to have anything but, direct access into it. Okay, so vector set is going to be, and I think that we'll just copy from here. It's going to be that. Okay. And then remember we have it as a primitive operation as well. So this is me vector set. And we're going to have vector ref. Which is going to just take the vector and the index. Let's move that up for consistency. I'm sorry, we have... Oh, right, because they're primitive operations, so they're going in this prim op. Note that we don't... it's a difference between Gleam and Racket here, in that we need to distinguish. We have this like singleton wrapper. It's kind of almost pointless from a like a semantic sense, but you can't just say, hey, here's a name. Like Gleam doesn't have anything like that, so we have to tag the contents of the argument to that operator. Okay, so vector set, and then we have vector length, and that's just going to take the vector. And we have global value. Okay, and we have the vector set statement, and we have collect, and then there's nothing else new there. Okay, so let's read. The output of explicate control is a program in the intermediate language C Tup, for which figure 612. Okay, so we looked at the abstract syntax there. The new expressions of C Tup include allocate, vector ref, vector set, and global value. It also includes a new collect statement. The explicate control pass can treat these new forms much like the other forms we've already encountered. The output on the rendering example shown on the left side of figure 6.15. So I don't remember which one this is, but okay, so this is the C Tup on the left side. This is going to assembly. So you can see here that this is probably a attempt to allocate, right? Right, so this is if we have to garbage collect, then you go here, right? And and then they both go to block 9. This is like construct a void and assign it to _4. And then it's, you know, allocate 1 vector integer and set field 0 to 42, and then assign that allocated thing to this new variable. And then we're going to do that check all over again. Can we allocate? And then we go, if we can, we go here and we do nothing. If we can't, we go to block 8 and we collect 16 bytes. And then we go to block 6, which is allocate the vector. And then set it to this inner vector that we created before. Remember, we're working on that. Let's see, we did a test of that wasn't it. I forgot which one we did that in, but there's a sample program which is like create a vector that contains a vector that contains an integer, and then deref down into that vector as well. Okay, so this is going. So we're going to allocate this, you know, one slot. And then it's going to set that field to the vector that we allocated before, and then it's going to deref it, and it's going to return the deref of that. So there's a lot of busy work in this one, but this is just to show like what would happen when you allocate structures dynamically. Okay, so then they're showing over here on the right. This is what the assembly would look like. I'm guessing that's after. Yeah, it looks like they've assigned registers here. So no, there's a bit with. It looks like they're putting certain things into specific registers. Okay. Yeah, I'll explicate control and select instructions. So hopefully we'll get to select instructions today. But what we've got to do is in explicate control, we're going to change this to ctup. And this is going to be lmon alloc. And this is going to be ltup. Okay, so now we're going to get a bunch of warnings here that we don't have. You know, we've got to fill out all of the other possibilities in this. So let's add missing. Okay, and I think that like we've done in previous chapters, I'm going to move the primitive operations so that they're up here next to the other primitive operations. Yeah. Okay, so we are in tail position. So in tail position, you always want to have a return. And then finally here we have blocks. We didn't create any blocks for that. And then it's going to be very similar here. This is, oops. So why does this not need any change? If you're in tail position, we're just translating the construct there. It's saying, you know, the thing you want to return is the length of the vector. So, and I should rename that so it's consistent. Okay. Except this is going to be vector ref. And we're going to do convert atom index. Okay. Because these don't require us to do any branching, we don't need to create any blocks on them. So do vector set. Okay. So that covers all the new primitive operators. Yep. Okay. Right, so this is an expression, and it's supposed to output a tail, right? Okay, so for allocate, I think that this is really just allocate. And blocks, we don't create any new blocks there. Oh, we need to do return. Forgot we need a return there. I don't, technically we need to cover this. But we should never be generating allocate and collect in tail position. So one could claim that this should panic. And in fact here, collect is a statement, not a tail. So I don't know that we need to I think what I'd like to do here is go we're going to put these into this, and I'm going to say panic as unexpected yeah, let's do it here. I guess we're not dealing with global values are only used right now for the dynamic allocation and garbage collection algorithm, so we should not be returning. We don't reference those at a high level. You don't ever see those. It's when we are lowering into, oh, now we have a language with allocation and garbage collection in it, that that global value appears. So it's like new semantics, or it's hidden semantics from the perspective of the programmer who's using the language. So I think it's fine to panic here. Let's see, unexpected GC internal in tail position. I think it's fine. Like, this is if we got this is an indication we wrote some previous phase wrong, I think. The others are actually, these primitive operators are semantics that can be accessed by the programmer. So those are fine to be in tail position. These are like, we did something wrong. So I think that that's pretty clear what to do there. It also saves us writing some code that just feels wrong. So yeah. Okay. That's maybe not the best panic message, but I'm okay with it. Okay, so now we need to think about we need to deal with the other steps. So in assignment position, let's add the missing patterns. So in assignment position, you want a tail. All right, and here you're past the continuation. In tail position, you are not past a continuation because there's nothing that comes after it. Right, so let us see. Okay, so if we have, let's leave that to do. Let's move the primitive operators up here where they're next to the other ones. Okay. Okay, so again, this is going to be similar to the one above it. It's going to be a sequence of an assignment. We'll assign, and this needs to be, we're going to call this vector, not v, because v is the variable. So we're going to assign v. It's going to be a primitive operation, vector length, and we'll convert the atomic. Okay, and then let's see here. So after that, we have the continuation. Is that right? And then it actually needs to be, let's see here, I'm getting dizzy with all the nesting. Okay, so this is supposed to return a tuple. Blocks. Okay, so the sequence has an assignment in it, and it assigns v to the primitive operation of vector length, and that has convert atom. Don't worry, this is going to reformat for us. I just want to get the parentheses lined up so I know what I'm doing. Okay, so then we have the continuation. Okay. And the rest of these are going to be very similar, so I'm just going to copy this. Let's copy it with the braces, even though we don't technically need them. Okay, so now we're going to have vector ref. And this we need to say vector. And this will have a convert atomic of index as well. Okay, and now we're going to have a vector. I should have called that vector or vec to begin with. V is such a common variable name. Okay, and here we need to say vector set. Convert atomic index, convert atomic value. Okay. Okay, so now we've got those defined. We need to do these last ones. So allocate can be an assignment position. You know, I don't, it's interesting that they say collect should be, Oh, well, collect is an expression. Yeah, I mean, we won't generate it in that position. I mean, I guess we could panic on it. Global value we should definitely have. Oops. So allocate we absolutely need to have. So let's see what we did before. Right, so we needed a sequence. Okay, so we're not going to create any new blocks. We're going to make a sequence. It's going to be assign the variable v to allocate amount t, and then continuation. Easy enough. And this will be similar, except it's going to be global value name. And this one, let me say unexpected collect in assignment position. We should not. What's wrong there? I have a syntax error somewhere. Put the to-do back and see what happens. Okay. Panic as unexpected collect in assignment position. Okay. Technically we could, but like the garbage collector is an internal bit. So we shouldn't have to deal with that. Okay, interestingly, oh, it's because we have panic here. We need to make sure that in predicate position, right. I think some of it is that in predicate position, that's like the conditional part of an if, right? So here we're saying what is acceptable in this position, and where it's a variable or fetch a variable that might be mutable, then we generate an if, because the if always has to have a comp in its condition position, so it has to have a comparison. Now we short circuit the literal true such that we don't generate the branches if we have a literal value. It's always going to be that value. On not, we call back in by inverting the branches such that the true branch becomes the false branch and so forth. For let, what do we do? Oh, right. So this is like right. We take the expression. This becomes the expression on the right hand side of the let becomes the contents of the predicate. And then we wrap that assign. So like this this new expression becomes the continuation, of this of the inner predicate. Or, I'm sorry, this becomes the continuation of wrap. So we wrap it with the assignment, right? So the assignment comes first, and then the if. And then here, this is the basic one. So if we already have a comparison operator in predicate position, then we're just doing the straightforward translation and creating blocks for the two branches. Okay, so if we have an if with an if in there, we have to spread that out. And this one I think was kind of brain bending, so I'm not going to go through it. We could also have a begin, which has a bunch of statements which are, their return values are ignored. I say statements, they're expressions, but their return values are ignored. And then the last expression is the result of this begin block. And so we say, okay, the result is going to be, whatever that result is going to be the contents of the if condition. And then we're going to wrap it with a bunch of, so explicate effect is essentially we're going to throw away all of those, the results of those statements, so they don't even impact the value of the condition, except for any side effects that they might have, like setting a variable. Okay, so what do we technically have here then? If we added, let's look at this, Elmon alloc. So we have vector length, vector ref, and vector set. As primitive operations. And we have collect, allocate, and global value. Let's go ahead and put in here I'm going to split bottom and scroll the expressions into view. So technically we have collect amount. I'm just putting them in here for consistency's sake. Just say this is what we're ignoring. Allocate amount t. And global value. Then this is so we could pull them up into here. Elmon, the thing that gives me a bit of pause is that vector ref could return a Boolean. Let's look at the primitive operations. And vector set. So vector length returns an integer type. Vector set returns void. I think vector ref is the only one that's valid here. And because it could contain a Boolean. So I think I want to treat it similar to like the variable, right? So here we've got, we'll say vector and index. So there's a question in my mind about whether we generate, or maybe what if we have generated our vector. Is vector ref a complex expression? Collect, allocate, and global value should be complex operand. It feels to me like, because what we want to get to is something like this. It feels to me like if we're going to allow vector ref in condition in the predicate position, what we need is this assigned to a temporary variable. And we can create blocks and labels, but we aren't generating variables here. And I wonder if we need to do something to remove complex operands. So like it's not required to be atomic. On an if. It's like the condition is an expression. It doesn't have to be atomic. This is an interesting conundrum. Like conceptually, this is the same as get me a variable. Like in my mind, that is conceptually what it is. But okay, so let's say somebody created a vector, and in the higher level, I mean, we could even create an example for this, that it wouldn't be that bad. So let's go up. We have some test up here. Let's see. Oh, these are not public. They have to be public if you want to run the test, Sean. That's fun. I wonder if these tests ever passed. They probably weren't even run. Whew. Okay. So like, I feel like, let's say a vector ref predicate test. Pub fun. Okay, so we're going to do something like let, we're going to say v1 is vector, and it's going to contain, why not just go with the flow, 42 and true. Okay, and then in that, we're going to say if is a vector ref, no, it doesn't bang. Okay, so vector v1 position 1, then we'll do, we're going to return 5, and if not, we'll return 10. So we've assigned a variable, and here let's just do vector ref v1 position 0. So the type of this should be let's just assign that to this, and we'll say p l.interpret should equal, so it is true, so we should equal 5, and then in value 5, right? The other thing is that we should do type check it. Type check program be okay. Okay, we have missing patterns over in here. So let's just put to do here. And then down here, we're going to add missing patterns and have it be a to do, and it'll just be a warning. Okay, so the tests pass. So this does type check. Now, if I said 0 here, it should not type check, right? So it expected a Boolean and it got an integer, because we do that has type wrapping, right? So, and if I did 1 here, it should also not type check because those branches don't have the same, they don't have the same type. Okay, so I think that convinces me it's okay from a programmer's point of view to have vector ref in that position. So what will be interesting is, what if we take this, we'll just do it in this test, and we're going to say p, let's see, that should be okay. So let's do we'll call it TP, and we'll say we're going to pass that to, what is our order of operations here? Show me the graph. That's always at the end of the chapter. Okay, so we have shrink, we have uniqueify, we have expose allocation, we have uncover get, and we have remove complex operands. So what I want to do is see what happens with that vector ref through all of those phases. So let's grab that and let's just throw it in here. Okay, so we get in here. Okay, so we've got uniqueified. So v1. So let v1. We're going to vec init. That's going to be assigned 42. Vec init 2 gets assigned Boolean true, and then we do our little garbage collection dance. Let temp2 is value of free pointer plus 24, because that's how much we need for this vector of 2 elements. And then we say, you know, is temp2, so is that less than the amount of space that we have left? Okay, if not, we return atomic void, collect. Okay, so here we're still in okay, so that's the condition of the if, which is all about this computation of do we have enough free space. Okay, so if we do, then we allocate no, I'm sorry, here. Right, so that's the if, and this just throwing away the result of that if. So we do have collect in assignment position. So I need to make sure that we but it's not in predicate position. Okay, it is in assignment position though. So because it's going to be assigned to the result of that. So I think that we need to go ahead and do this. Hello, Sam Art, nice to see you. Welcome to the stream. Okay, so I need to fix this, and then we will go on. Okay, so we're going to see c.collect, except it's a statement. So really, I think what we assign here is c.void, right? So we actually have, we're not creating new blocks, so we'll continue with that. So we have 2 sequences. We have our first statement, which is collect, because that's right, that is a statement. And then we assign void. Interesting. Okay. We assign void to that variable, and then we have the continuation. Oh, C, what is it? C.atomic. Yeah, C.atom. Okay. So we assign void to the variable that we're trying to assign after we've collected, and then we do our continuation, because collect doesn't have a value. Okay, so the question we were trying to solve was, can vector ref go into that if position? So if we go down here, right, so here we are, this is the program we wrote, right? It's just construct a vector. Sir, I am from the United States of America. I live in Kansas City, Missouri. Where are you from? And welcome to the stream, by the way. I hope you enjoy Gleam, as I do, because that's what we're doing. And we're working through this book called Essentials of Compilation. We're in chapter 6, just for reference. Thank you for coming to the stream. Okay, so you're from India. Welcome. That's a long way away from here. Welcome. Okay, so we created a vector, has 2 fields. One of the fields is a Boolean. And then in the condition, This type checks because dereferencing this field, the field 1 from this vector, gives you a Boolean type. So it's fine in this position as the predicate. And so we need to handle that. Here's the output of all the phases before the one that we're working on. And we went over a lot of this stuff. This is generated code. So in the end, we have this. And we have vector ref in predicate position. So I think that we need to adequately handle this in explicate control. And I feel like we need to make a case for it. What is this code for? So this is we're working through, like I mentioned, we're working through a book. This is just a side project. I'm having fun. It's called Essentials of Compilation. So you can go, this is the repository we're working through. Or this is where I'm pushing my code to. If you go to IU compiler course. Right, so we have this one open. Let me get up to the top, and this is where the book, and it's freely available. So if you go to here, they have releases which contain the PDF. So you can download the PDF. We're working through this one, which was October 2023. It doesn't have, give me just a second. The PDF, of course, does not have the fancy cover like this. I have the hard copy. It's just easier to work through the PDF while I'm on the stream. But this is the book, Essentials of Compilation, an incremental approach in Racket. So the premise of it is that you can start from a very simple language and build the compiler top to bottom, and then add features to it as you go. And so what we've done in chapter 6 is added structs, so vectors, tuples, whatever you want to call them, to our language that already has conditionals, it has loops, it has booleans and integers as the atomic data types, and we've added vectors as another data type, which is a composite. So that's what we're doing. And let me see, yeah, we can just close that. Okay, so back to the problem. We need to handle this construct properly. So I'm going to go ahead and save that. Let's go back to explicate control. So in this position, I feel like what we should be doing is ultimately we want a comparison here. Or do we? Like, because we have to generate, you know, when we had a variable or a get bang here, right? Like these are assumed to be Boolean typed. So we just compare them to true. And I think that what we need to do here is also compare the result of this expression to true. But this is a whole expression. This is not atomic, and it does not contain the comparison primitive operator. So, and like we were able to get away with doing things with not, right, by and lets by doing assignments, but for not all the comparison operators, and here was like we have to unwind some of it because it branches twice potentially. Oh, am I working? Yes, I work for a company called Grok, G-R-O-Q, but it is not at all related to the stuff that I do on my stream. Grok, we build AI inference hardware, and we run a public cloud that hosts open source models that run on our hardware. It's a really interesting set of hardware, and it's a really exciting time to be working for the company because we're growing like crazy. But this is not at all related. I do this for fun. No, it's not. GROQ predates the GROK that is part of Elon Musk's X. So we're not related at all. The founder of GROQ, the Grok I work for, was on the team that built the TPUs at Google. I think he led the team, if I recall correctly. But that's a whole different topic. We're doing compilers here. Okay, so vector ref in this position, I feel like we need to generate an assignment, which means we need to figure out, maybe we can generate a label based on the number of blocks. I feel like that's not right. By the way, this is a company I work for. Because we're not creating a block. But we need a way to know. We need to generate a variable here, and I didn't expect this. I feel like it should actually go. Maybe what we do in remove complex operands is we treat that, we get around this, right? By treating that as a special case on the if. How can we do that? When we're in RCO Atom, we are generating bindings. Something fell. Okay. So here. Right, so we do this new variable, right? And I think that we should do a new variable here. The thing is, this is not an atom position, so interesting. Okay. Right, so it's a binding. I wonder what the implications of this will be. Well, let's see if we can hack it. So if the condition is and then we'll have if true, and I need to make sure that I get this syntactically correct. If false. If it's a vector ref, so we have v and index. I think that what we want to do let's look at where we do this. Do we do anything special for vector ref as a primitive operator? Okay, here we go. So we should call into this on this operator. Okay. So yeah, let's call. We're gonna say this is the condition 1 and the counter 1. We're gonna call RCO expression, and we're just gonna reconstruct this. Yeah. Hello, welcome to the stream. I know some Python programming. Can I get a chance to work with you? I'm not responsible for hiring at my company, but I appreciate the question. So we do have some positions open. Please feel free to apply. I don't know that we are hiring in India, but I can't guarantee that we're not. So thank you. Okay. So what I'm doing here is I'm making sure that we are making all of the stuff atomic in this expression. And here's the updated expression. Now what I want to do is we're going to do something similar to what we did in the where it is in atomic position. What we want to do is generate a binding. Right, so if we go to where RCO atom is defined, what we're doing is we're saying here's the new expression. So like where we have a binding, here's the new expression, here's what the binding is, and then we're replacing so we're generating a fresh variable, and that's what we replace by generating lets. So what I want to do is generate a let that wraps the if that we're looking at. So we have made sure that all complex operands are handled inside this vector ref. So if V contains a complex expression, you know, now it's down to its atomic. So I want to generate, let's make a new variable. Except I need to look at the other if, and we basically need to do this as well. What's going wrong? Did I miss a paren there? Yeah, I got those messed up. Excuse me. Okay. So let's do a fresh variable, and we're going to say var counter 4, new variable, and we'll pass it counter 3. I don't really have to name these different. We've done shadowing and other ones. It's fine, but. Okay, so now what I want to do is from this position, I'm going to return a let, which is going to be var is the value of C1. And then inside that, I'm going to generate an if, which has var as the condition, except this needs to be lmon. Var, and this needs to be wrapped with an atomic. I don't know that this is the right solution, but we do variable generation injection in this phase, and I don't want to do it in a later phase because we don't have the mechanisms for it. So I'm going to special case this one. This is a valid condition, but what I want to do is treat it as this has to be extracted. I don't want to deal with it at this phase. And then if I'm here, then I don't have to handle that. I've already extracted it into a binding that happens before the condition. So that's why I'm doing that here. It feels a bit janky, and I'm going to put a note on here. If we don't extract this into a new binding here, we have to deal with it in explicate control, where we don't. Now, this could be, maybe this is wrong. Maybe this is wrong, because maybe what that vector ref lowers into is in the assembly, we might have something like, and I'm going to get this wrong because I don't know, but we might have something like move this vector ref v with an offset of something. How do we do that? Or it'd be like v like RAP, something like this. Let's just say move into RAX. It might be something like that. That's what vector ref would be. And it actually might be, it'd be like, like 16 RIP or something like that. I don't know. I don't know what this, like, if this is a problem. And then you could do comp 1 RAX, right? Comp Q. Honestly, you could even, I don't know if it would generate the right thing, but you could even do like that potentially. I don't remember if they have to be in registers or not. But the main thing to get here is that, this index is going to be like a static integer in our code. We don't have in CTUP a concept of this variable plus an offset, which is essentially what vector ref is. Okay, so we did this. Let me think about this. Let's go back to the explicate predicate and look at the stuff we're doing here. And it comes down to this has to be atomic, but vector ref is not atomic. Should it be is a big question. If we look at the additions to, going back up, sorry, we got way out of position here. So this is, we didn't add an atomic for vector ref. Like, it's a primitive operator. It's not one of these. So it can't go directly in the arguments to comparison, right? Um, but when we're here and we're in the predicate position, we have to deal with the fact that the contents of if, sorry, I keep flipping to the wrong one. You can see here if has to have a comparison operator in it in the condition position. So in the predicate position, it has to be comp, basically. And here we're comparing a variable to the value true. Here we are saying this is the variable, or this is the static value, so we don't even need to generate branches. For not, we're just inverting it. We're inverting the branches. For let, we're making the assignment and then applying the predicate. For comparison operators, we just say, okay, well, we're going to do the comparison. If we have an if in that position, in the condition position, then we do one if and then we do the other, basically. And it creates this kind of diamond-shaped thing. And, you know, for begin, we apply all of the effect position statements, and then we apply the result as the condition. So so forgive me if I don't seem like completely clear on what the right solution is here. My gut tells me we should be able to use vector ref in this position because you can contain booleans in a vector. But how do we turn that into this? And I think that we have to keep this in here. We could plumb in all the possibilities of generating fresh variables into explicate control, but that feels kind of bad. And I actually wish that their example in this chapter handled, or they had an example of vector ref in that position. Right, like note that in the monadic neural form, it's just an expression, which is fine. And we have all the, you know, the primitive, you know, they still have this typo here. I need to talk to the author. They're missing some expressions, but if can contain expressions in condition position. And one of those expressions can be vector ref as a primitive operator. So, yeah. I mean, the other thing that we could do here, rather than handling this, is turn this into a comparison and just recurse, which would be fine, because then that would force this. Yeah, let's do that. I actually like that idea better. So let's turn this into, we're just going to call this RCO expression. we'll pass it counter as the second argument, and we're just going to transform this. That feels better to me anyway. Okay, so this is going to be elif, and we're going to have primitive operator comp. Okay. We're going to say EQ, and then I'm going to copy this in there. And this is why I love recursive algorithms. You can do all sorts of crazy stuff like this. Okay, so then we're going to say this is a bool of true. So we're what is wrong? There's something wrong here. What I'm doing, let me make sure I get this lined up correctly. Okay, so I'm taking this raw deref this, and I'm going to turn it into compare the value of this. Oh, here, that's where I'm missing it. Compare the value of this, derefing this field of a vector to the Boolean true. And now we can say, well, this comp is going to be, it's going to, when in this transformation, it's going to require atomic arguments. This is not atomic, right? So this is going to get pulled out into a variable automatically. This is atomic. And then what we'll have is the let binding, and we don't have to deal with it. So not my favorite thing. I feel like in some ways when we lower it to assembly, we won't need that binding. But that binding is going to get assigned a register, and it might get assigned, the register just goes directly into comp, which is fine. So I think it's going to be okay if we do this. So vector ref. Okay, yeah, I don't think I need to write anything more about that. That's just so I remember why is this special case here. But I think it's important. Okay. All right, back to exploit control. So I think we've dealt with all the cases for predicate position. Again, here we're assuming that if we call collect or allocate or global value in predicate position, something's wrong with our program because those are generated by us. Vector length and vector set will not type check in that position, so they should not. It's fine to panic there. It should have been caught at a higher level. Okay, so now down in effect position, let's fill all these out. Kind of pointless to. Let's see. I don't think we need to create blocks in effect position. Okay. So allocate. What is this going to return? We have. This is we're past the continuation, right? Yeah. Okay, so at the very least we need to handle the continuation. So allocate is an expression in effect position. Why would you allocate something and then throw it away? Honestly, I think that we should panic here. As unexpected allocate in effect position. Now collect is fine to have in effect position. We have a sequence because it is a statement, right? Amount. And then we'll have our continuation. And then we'll return our blocks. Global value. So set bang is fine. Let. You might still do that for effect. Yeah, I think we should panic here. And we need to make sure we ignore those fields. You know, I really would prefer not to panic in most cases. Oops. But we have a situation where these values, these expressions are never written by the programmer. They're written by us. They're written by the compiler. So if we're allocating memory in a spot where we're just going to throw it away, we're not capturing this. This is not assignment position. We're not capturing the value of this. Then what the heck are we doing? Same with referencing a global value, which is like our our heap pointers. We should not be doing that. Okay, so I think we've updated everything in here that we need to update. Yeah. Similar problem that we talked about up here, like when we're in tail position, which is what is the return value of our program, right? We should not be calling allocate or collect or global value, because those are generated when we want to allocate a new tuple, a new vector. Okay, let's go to the tests. I think that we have. I don't know why this is commented out. Oh, it's because parse no longer produces a while. Yeah, that's why it's commented out. Okay, so now we're going to go into explicate control test, and we need to basically uncomment all of this. Why did you not uncomment? And we're going to update it. I've got the problem here is I've got multiple comments. And so it's like, do you want me to uncomment or recomment? This is just what it looks like, what we're expecting this to look like. So, and then here. What the heck happened here, folks? Wait, why did... I have that test. Why? Oh, did it just duplicate a bunch of stuff? Maybe that's the problem. Maybe I accidentally used that, like, alt down, which I do love, but it creates problems. Okay, let's see here. We got the basic one. We've got if eliminate constant conditions, let inside condition, shrink conditions. We got some good tests in here. Except we've got these things defined multiple times. Yeah, so like let me go from here. Yeah. We need to eliminate the duplicates. How did that happen? Oh, Jesus. Okay. Uncomment this. Okay, so now... What? Is my editor going wonky? I might need to restart my editor. I think something is going really wrong here. Okay, we're going to exit and we're going to restart. Because I feel like I'm going crazy. I don't know about you, but... You know, the other way we can do this is we have all these. Let's just delete everything to the beginning. Okay. Okay. So now we're getting the things that we should get. So we're going to say this is C-tup, this is Lmon alloc, and this is L-tup. And now let's find what the problems are in this. Let's expand everything. Okay. We're down to 3 errors, 3 compiler errors in here. Okay, so now this is a problem of, remember we had written a lot of this by hand before I had the parser, so like the front end of the compiler. So I think that we did not use this parsed thing very much. We started doing it here because it was too onerous to write out the syntax trees of some of these things. So I think that what I want to do is we're going to pull all of this into parsed. And again, we're going to follow what we did in this one. No. What test was it in? Were we in remove complex operands test? Probably. Yeah, so we need to do all this business. So we're going to do that. Okay. Okay, so we need remove complex operands. So now, let's see. So say, what is it saying? It found lmon.program. Oh yeah, so we need to make sure that we're returning the right thing. And we need to import that. Yep. Okay. Tests make me smile too, Amos. Like, I actually did myself a favor by having all these tests for the previous chapters that I can just re-enable when when I've got things. So here, we're gonna get rid of the extra business there. And what else is wrong in this file? Forget that for a second. Oh. Here. Okay, so we had defined P, right? So I need to duplicate that up here. So let's go to the bottom. Basically need to do all of this. And maybe I should put this into a function. That I can call from both places, but where is that error? There it is. Okay, so we're just gonna throw all those in there. Okay, so this is probably gonna fail now. Okay, so those passed. That's cool. Let's go down and we're going to use our example that we were testing a moment ago, like this stuff. Right? This was the program we got. So I think that what I want to do is in the remove complex operands test, we're going to add a new test here. Let's say what do we call our test in here? RCO. Okay, so we're going to say RCO transform vector ref condition test. And what I want to do is how do I want to do this? This is a simple program that has a huge explosion of syntax. Okay, so let's at least get this. And we're going to say, so we will have gotten to parsed. I'm going to say let p2 is this, and we'll figure that out, what this should be. Remember, this is the remove complex operands injects these temp1, temp2. So I think that what we need to do here is transform this. So 1, 2, 3. We need to transform this into it's down here. So we're going to have a let, which is going to be temp4 probably. And then we're going to say it's going to be this. The if is going to go inside here, and this is going to be prim comp. This is what we did earlier. EQ var temp.4 bool true, right? This is what our transformation was supposed to do. So so now I just need to label all of these. So what we ultimately want to do is say remove complex operands should equal p2. Okay, so now I need to go through and slap all of this stuff, all of the qualifications on it. So I'm going to just type it once, and we're just going to paste. And this is way exciting, I know. So riveting. Don't you just want to do this? All of this monkey business of typing. You're like, wait, Sean, you work for an AI company. Why aren't you letting, an LLM do this for you? It's an excellent question. I don't know the answer. Probably because I'm a troglodyte who likes to actually write the code myself. Remember the types come from the original language, not from the intermediate languages, so we have to refer to them separately. So what I'm hoping is that when we're done with this, we will be able to, this is all tup, we will be able to look at the code generated for our example here, and there we go. Okay, so now it's happy. Let's run the test and see how wrong we are. Okay. So this is what we expected. Here's what we got. What's the difference? And I'm just going to paste it in here and let it be reformatted. Oh, okay. So it put it inside, which is actually okay. And I get why it does that. So we're just gonna fix it. This is one of those things where like my brain and the compiler don't necessarily work the same way. And we're gonna have to figure out how to rearrange that. Okay, so the if comes out there, the let goes inside, and then we do, okay. So that's actually what it turns into. It's fine. Note that in explicate control, this is going to be extracted anyway. Okay, so let us not delete too much, Sean. Okay. So I think that I feel pretty, there we go, that makes more sense. Feel pretty good about this. Let's run the test again, make sure we fix that. Okay. You know, at some point this gets too complicated to do straight like AST comparison. I don't know what we're gonna do. We almost need some kind of way to look at particular parts of the program without specifying exactly the entire structure, and I don't know how to do that yet. I need to think about it. We might need to do some kind of like, what do they call it? Key value coded traversal. That would be okay. Maybe we can implement that at some point. Okay. So what did we just, okay, so we cleaned this up. We don't have all the duplication anymore. We're gonna make a new test. And what I wanna test is basically what we just did over here. I wanna test this. And we're gonna call it explicate control vector ref condition test. Okay, so that's going to be parsed, and we have stuff from here, but what I want to look at is what is the equivalent in our C-like language. So what do we expect it to look like there? I'm not gonna lie, this is not gonna be easy. So let's split right, and we're gonna look at this, and we're gonna try to do the transformation ourselves. Won't that be fun? Okay. So the other thing that we're going to need here, and I might just hide the project browser so that we can see it. We're going to close that in this window. I need to split bottom on that so we can see that at the same time. All right, so I'm going to do another one of these business, and let's make sure, yeah, it's just going to be C dot. The thing is, this is going to be, let's get the problem is this is going to generate blocks, right? Because we have an if in it. We have multiple ifs because we've got honestly, I think that what I want to do is cheat. So we're going to do explicate control, and we're just going to echo. And we're going to run that test. Let's see what happens, because I don't know that I can, in the next 15 minutes, conceptualize all the things that need to happen to translate this into C code. Like we could try it. The problem is we've got an if here. For allocate, it's inside the allocation of that vector. We're doing the garbage collection. Do we have enough free space, etc. stuff. And then we got an if down here after we've allocated all of that. So we're going to have a bunch of blocks created. How do we want to do this? Let's see what we get when we run explicate control. But I think it's going to be a lot. Now, what we could do, actually, as a better test for now, is where's there is example. So their example looks like this. We can, why don't we do that? I like that better. Because we can, it's going to be tedious, but we can mechanically translate this to our abstract syntax tree. So remember, this program is vector ref of vector ref of vector of vector. Oh, let's see, this program is so ridiculous. 0 and 0. One, two, three, four. 1, 2, 3, 4. Okay. Okay. So yeah, let's remove the split here, since I'm going from the book. So what we could do is say I never understand how they skip. They're probably, when they're allocating this business, they're probably using the same counters. I don't know. we're going to get a lot of mismatched variable names. But what we should get is the same number of blocks with the same, essentially the same contents. Okay, so right, so what we did was something like this. Okay. So we're going to make a C program. It's going to have an empty dictionary for the first part of it. Okay, and then we're going to have from list. And this is going to have start is going to be something. We'll do that in a second. We're going to have, let's start with that. Let's just go ahead and do it. So we have a sequence. And our first statement there is an assign. And they're using temp9. I know this variable is going to be wrong. And it's going to take, that's going to take an expression, which is going to be a global value free pointer. Okay, and the next one is going to be assign. I'm sorry, it's another sequence. Assign temp 0. I know that variable is going to be wrong. It's a primitive plus variable temp9 int 16. Okay, and then we're going to have another sequence. Assign temp1 is global value from space end. Okay. Actually, it's not a sequence. We're going to have if. If is a tail. Okay, and it's going to be prim comparison less, that's going to be L2 dot less than, right? Variable temp 0, variable temp 1. Okay, and then we have go to, yeah, go to block 0, block 1. Okay. So I know this is going to be wrong, but let's see if we at least get somewhat of the start block correct. So let's say P pass to explicate control should equal, no, should equal P2. Okay, I know this is going to be wrong, but this is a start, and we can build on it. Okay. Untagged vector initialization. Okay. Vector ref test. So, where did I say that? Untagged vector initialization. Okay. So we have a problem in our compiler. Is it that, oh, I know what it is. Here, we need to be doing this. Hooray! Okay. So now at least we're getting, hey, it's wrong. Okay, so what I want to see is, obviously this is different. What I want to see is what the start block looks like. So I'm going to just dump this in here. We'll save. Okay. So here's start. Right, so we have a problem. We get to... No, I guess not. I'm like, why is this a... No, we just assign 42 before we even go into any of the can we allocate. That's hilarious. Okay, so then it's going to block 5 or block 6. We are seeing the temporary variables, they're numbered differently, but they're coming in the same order. So I'm okay with that. So it either goes to block 5, okay. Void, go to block 4. 6, and then 6 is collect, and then assign nothing to underscore 4 and go to block 4. Okay. That's interesting. Okay, so let's see what's in block 4. Here's block 4. Block 4. Okay, so we're allocating. There's alloc 2. And then, so we did this vector initialization was what we bound inside start. We bound that variable. And so we're assigning that to field 0 of that allocation. And then we are assigning that allocation to vecinit 5. So we've got a little bit of, this will get removed in the register allocation phase because it'll detect that these are not in conflict with one another, or they're basically the same, and so you'll get a move from one position to the same position, and then that'll get eliminated automatically because it's a no-op move, right? Okay. But basically, these would be not live at the same time, and so they can allocate, or they can be assigned to the same memory position. Okay, and then, right, so then we're checking, can we allocate, doing the same business again, and if we can, we go to block 2 or block 3, and the block 3 is like collect, and so forth, and block 2 does nothing. And then finally we go to block 1. And then, so then we allocate the vector, we assign that variable into field 0, and then we move it into this temp.7, and then we assign temp.8 vector f of 0, and then we return vector f of 0. So like this is actually what I would expect. If we look at what's being generated, and of course these are, they're not coming out in the same order, but what I want to check is semantics, and if we're okay with that, then I'll just fix things. But let's look at what they do over here. So we already looked at start. The main thing that's different is that they go to block 9, and remember that previously in the chapter, I was like, how did they inline that literal 42 consistently? They don't say. It feels like an oversight, and it's fine, but you can see here that what happens is we get a different shape because I'm trying to make sure that values, whether they're, you know, literals like this or they're variable references, that they get stored into a consistent name that we can fill in the vector with. So yeah, I don't know. Note that there's this vecnet 6 right here. There's like this vector that we allocated. We have something similar here. We have vecnet 5, right? And that's where we allocated that. All right, let's step through it real quick, and then I'll try to see if we can fix our little world here. Okay, so start. Again, the main difference is that we assigned that field into a variable before we checked whether we can allocate. The allocation looks basically the same, different variable names, of course. Temp1 gets free pointer, temp2 gets temp1 plus 16, temp3 gets from space end, and then we compare the penultimate two, and we go to a block or we go to the other block. Okay, so their block 0 is our block 5, their block 1 is our block 6. So let's go look at block 5 is assign 4 void and go to block 4. Now, interestingly, I don't know that they deal with this, but remember they said that collect is an expression, not a statement. And maybe we could eliminate this, assign to _4, because it's just going to be thrown away. I want to look at where we did that. It would be an explicate assign. Right? So, I mean, we still assign void here. The thing is, though, do we even need that? I mean, we can do what they did. Just go, hey, this is going to show up in assignment position because we put it, that's the code we generated. I don't know the rationale for that code. Like, why are we not just throwing it away using begin, right? All right. Let's do what they did. And I'm going to put a little note here. It says, this essentially throws away the assignment. But collect is generated from the compiler, not the user. So we can discard the assignment. I think that part of it is that in the higher levels, that let, so this is expose allocation that does that phase, right? That let ensures that the garbage collection stuff happens, like it's a sequencing thing. It ensures that it happens before using the newly allocated variable. Now, I think that they could have done that with begin and not with let. Personal preference, but we know that we can just throw it away. So this will align our output with theirs. And let's go back to the test. But if we eliminate that, then we'll get let's just update that. We know that that's what's going to happen there. Okay, and you know their block 5 looks the same, or their block 1 looks the same as our block 5, or rather there. So we even get the same underscore variable name. Okay, so their block 9 is our block 4 for whatever reason. And then when we walk through this, I'll wrap it up and we can continue next week. Okay, so they're not. This is allocate the vector, or vector of integer, just one slot, and then we'll assign underscore 3. Again, here this is a let originally that I don't understand why we need a let. We could do begin, because all of these vector sets return void. We don't need to assign a variable to it. That variable's never read, right? So I don't know the rationale there. Maybe it's possible that there's something later in the book where we actually need those bindings, but I can't imagine what they would be. Maybe we'll find out. Okay, so it's setting field 0 to the binding that we made originally in start. They don't do it in start, they inline it. So that's the main difference we have there. And then they're assigning that to a new vectornit variable, because that's going to go in the slot of the outer vector. And then again, we're doing the garbage collection dance. Okay, and we say block 2. Now, I think that the numbering difference here is kind of a difference of what order we come in and are using the same counters for variables as blocks, and I don't know how they skipped 2 through 5 in this situation, but whatever. Okay, so block 2, again, that we remember we can remove this since we just adjusted it to be the same as theirs. It's just collect and then go to. And then finally block 1, which is the last one. So allocate a new variable, assign vector set, right, field 0. This is all what we would expect. I'm not seeing anything weird here. Okay, and then you deref it into a new variable. All right, no, this is assigning, so we assign this to right. Again, here's a difference where, like, if the code is consistently generating, you would expect, like here, it gets assigned. There may be something I'm missing that it's like, oh, well, we don't need to do that reassignment. Ultimately, I don't think it matters because it's going to get eliminated. I sometimes wonder whether they did these examples by hand or whether they actually use their own compiler, and like whether mine has bugs in it or theirs has bugs. I'm not sure. Okay, and then finally, so we're assigning to a variable the deref field 0, and then we return the deref of field 0. So I feel pretty good about this. We don't need to do that. In fact, I'm going to delete all of this. I feel confident about we're just going to have to put, let me see if I can. Nope. Yeah, see, I could do fix with assistant, but it'd be like, what the heck language are you using? Okay, I'm just gonna slap these in here as fast as I can, and then we'll call it a day. Okay, so that means that next time, well, I'm doing this very mechanical thing. Next time, what we can talk about is what I wanted to get to, but I felt like it was important that we test this and we think all of this through. Oops. We're going to do the select instructions pass, which will be interesting to see how it differs, because we are now going to be having to distinguish between things that are on the stack and things that are on the heap, or things that can fit in registers or not. Remember that the allocate call returns a pointer, basically. And the things on the heap will be tagged. So we're going to have to construct those tags. Now, technically, I think that the student support code does that. And maybe what it would be good to do next time is to look at that student support code more closely. And when I say student support code, it's just like the stuff that they don't make you implement if you're taking this as a class. And we can go in there and look at what the garbage collector does, and also especially the allocator. And the allocator, we're passing the types, we're keeping the types deep into here, because the allocator needs to properly tag that value on the heap. And that tag is 64 bits, and we described it earlier in this chapter. All right, now that I've tagged all that, let's run our test and see if it works. Okay, so we got what we expected. Cool. And I'm going to say chapter 6.5, explicate control. And I'll push. So we'll look at select instructions. We'll look at the C code. I've had it up here this entire time, and we can jump to like copy vector, and there's actually multiple because C is a single pass compiler. Where is it? Anyway, so we'll be translating. If you look into this assembly code, we'll be translating the alloc into, it should be a call. So let's look for alloc2, allocate. See where they're doing that. Oh, interesting. No, so what they're doing is, let's see. Right, so we move the free pointer offset by RIP into R11. Oh, and then this is you add 16, so it's like moving the free pointer. And then so that the next allocated thing will be 16 bytes beyond what it is right now. And then this is the tag. So we've generated the tag as 3, and we're putting it into slot 0 of this pointer. So basically the first 8 bytes. Okay, and then this is the pointer. So then we move that into this variable. Remember, this is assembly with variables. It's not flattened. We haven't done haven't done register allocation at this phase. And there's some, there's some spurious moves. Move into this one and then move back into that one. And now note that what it's doing is it's saying, okay, we're going to move 42 into 8 bytes past where R11 points to. So we have that whole deref thing going on. We at first used only deref with RSP, like for allocating things onto the stack, right? But here it's, oh, our register contains a pointer and we need a deref on that pointer. Okay, so that's going to be interesting. And I think that, yeah, okay, so here's the call to collect. Allocate is just, here's some instructions, right? We just need to go from where's the free pointer and, move it that many bytes. But collect is complicated, and so it's actually a call. Okay, so we're going to do that next time, hopefully, and we'll dig into the C code that is in the support library and learn a lot. So thank you for attending, and thank you for the interaction in the chat. Samart, I hope you find a job that you're looking for, and good luck. Thanks for coming to the stream. See you next week.